Hello friends, in this video let us solve one more question which was asked in GATE 2020. So here using incremental low frequency small signal model of MOS device, we should find the Norton equivalent resistance of this circuit. Okay, that is we should find the resistance seen from this terminal. Okay, because it is given that low frequency analysis, so the capacitors all the capacitors will be open circuited in the small signal model. Okay, so before trying to solve this problem, let us do some more problems so that we can be habituated to this type of analysis. Okay, so you can see that a MOSFET, it has three terminals: gate, drain and source, right? So if you are looking from gate, the resistance will be infinite because the gate current is always 0. Okay, now if you are looking from the source of the MOSFET, the resistance will be approximately equal to 1 by Gm. Remember that. So if you are looking from the drain of the MOSFET, it will be approximately equal to 1 by RTS. So the thing is, when you are looking through the drain of the MOSFET, it will provide you high resistance in order of RDS. And if you are looking through the source of the MOSFET, generally it provides you low resistance, that is 1 by Gm. But if you connect a load here, then it can provide higher resistance than 1 by Gm value. Okay, but if there is no load connected to the drain, so the resistance provided saying from the source is 1 by Gm. This value will be very low, right? Because Gm will be very high for a transistor. Okay, now let us do some more configurations where now let me connect a resistor right here. Okay, and here let me connect a resistor at the source. Now again, if you see in this circuit, if you see from the gate, the resistance will be infinite because gate current is 0. And if you are looking from the drain of the MOSFET, and this value is R, if you are looking from the drain of the MOSFET, remember that this value R will be multiplied by intrinsic gain of the MOSFET, okay, plus R plus RDS. So this is the equivalent resistance when you are seeing from the drain of the MOSFET when a resistor is connected to the source. Okay, so the source resistance R will be multiplied will be multiplied by the intrinsic gain of the MOSFET, that is GMRDS. To that value R and RDS are added. So this is the equivalent drain resistance. Now similarly, when you are looking in this circuit through gate, its value will be infinite. And now when you are looking from source, this value is also R. The answer will be RDS plus R by 1 plus GMRDS. You can see here the drain resistor is divided by the intrinsic gain of the MOSFET approximately, but in this circuit the source resistor R is multiplied by the intrinsic gain GMRDS. So in this way you can remember this formula. So please remember these two formulae, these are very important. So once again let me repeat that. When a resistor is connected to the drain of the MOSFET and you are looking from the source, that drain resistor will be approximately divided by the intrinsic gain of the MOSFET, but the actual formula is this. The source resistance will be RDS plus R by 1 plus GMRDS. And similarly, when a source resistor is added and looking through the drain of the MOSFET, the equivalent resistance will be R into GMRDS plus R plus RDS. So using this circuit formula, can you tell me what is the Norton equivalent resistance when looking through the source of the MOSFET? That will be simply equal to RDS plus R by 1 plus GMRDS. Okay, you can solve this using small signal model and doing all such stuff. But if you remember, these three cases, most importantly these two cases, it will be very easy to solve many more complicated MOSFET circuits. So I am suggesting you to by heart these two formula. Okay, that's it guys. Thank you very much.